Log on, tune in, find out. Another good idea from Cambridge.
Mugnolo. Thanks. So I was invited here by Malcolm Brown, so I wanted to say thanks to him, even if he's not here. It's a great honor for me to be here in Cambridge at the Newton Institute. And before I start, I wanted to add that this is a joint work with Serge Niquez from Valenciennes in France. So this is a joint project we have started some 6 months ago now, more or less. So, well, let me start this way. So assume you have a diffusive system. So I have a system with some physical system, typically with some mixture of two or more elements, and they are mixing. So it's well known that the typical mathematical description of that is given by the diffusion equation or the heat equation in the easiest case. And well, if you consider an infinite domain, so the whole space, or if you consider a bounded domain with some no flux boundary conditions, then of course you would expect the mass of the system to be conserved over time. And in fact, you can prove that. This is one of the classical results of a heat equation theory, and in operator theory, people say that the semigroup governing the system is in fact a stochastic semigroup, meaning that the total mass is conserved. Okay, so some 50 years ago, more or less, people working in applied mathematics, mechanics, and so on, started thinking whether it is possible to see this this property of conservation of mass as a generalization, if you wish, of say Neumann boundary conditions, for instance. So Neumann boundary conditions for a bounded domain are the typical conditions implying conservation of mass. So what if you drop boundary conditions, at least partially, and then assume instead to have conservation of mass? And instead, you can well, you have to impose some integral condition, and this is what people actually started doing in the 60s. So you have, say for the heat equation, it was done first. You have your typical boundary, your typical heat equation on a bounded interval, and then you complement it with so you problem, or well, Cauchy problem, you complement with this condition. So assume that you have a mixture of two elements. This means that the unknown in the system is the relative density of these two elements, and of course if you integrate over space, then you get the total mass of the system. And if you just shift your unknown, so to have in order to have 0 at start at the as initial mass, then of course this condition means that the mass is conserved over time in particular. And well, if you just think a bit, of course, for a heat equation with standard boundary conditions, then you need two conditions. And of course, the reason is that if you want to solve the elliptic problem, so the eigenvalue problem, of course, you need two conditions to specify an eigenvector. And well, this condition is, of course, just one. So you are just losing 1 degree of freedom. So this is not enough to have a well-posed direct heat equation. And in fact, people had to complement this condition by say, Dirichlet or Neumann conditions in one of the endpoints. Okay, so the beginning of the story goes like that. So Cannon showed in the 60s that the system has them, so the heat system or diffusive system with this kind of boundary conditions plus integral condition has some nice features, and this result was kind of forgotten, as far as I know, for a couple of decades, until in the 80s several people in Russia started working on that again, and well, they were able to play a little bit with Sobolev spaces, and it was possible to show that a solution exists for the heat equation with this boundary with this condition. Well, basically, the idea is to consider suitable test functions, integrate by parts in the parabolic cylinder, and to get some a priori estimates, and then apply some compactness method. And this paved the road for several investigations based on application of Galerkin schemes. And at the end, Peter Shi in 1993 was able to complement results by Yurchuk, and so at the end it was possible to prove that at least in some suitable weighted Sobolev spaces the heat equation is well posed. Okay, so now I want to tell at the very beginning, so everything in my talk is related to the direct problem, so I'm not presenting inverse theory. In fact, I'm not aware of any inverse problem related to the well, not of any inverse problem, but of anybody who's worked on inverse problems related to this kind of partial differential equation with integral conditions. So actually I would be happy if you could suggest me some related inverse problem. Okay, so so this is pretty much everything which is known for the case of mixed boundary conditions, so local and non-local. But in the meantime, it had been already discovered that the heat equation has other invariants. I mean, it is known that if you have, say, so for reasonable boundary conditions, for instance, for Neumann boundary conditions, if you have conservation of mass, which, as I said, so in many cases you have, then you can also deduce another invariant, which is the conservation of the center of mass, so the barycenter. And so,
but excuse me, I don't understand something, because in this case, if you integrate the heat equation from 0 to 1 and you use this, and you said you're given Neumann boundary condition at x equals 1, then this immediately gives you the other Neumann boundary condition at x equals at the other point. So this immediately reduced to the usual Neumann problem.
Exactly. So I mean, the idea is that
why do you pose it this way, as opposed to saying this immediately becomes the Neumann problem?
Yeah, but you can also say the other way around. I mean, if you have Neumann at both endpoints, yes, you also get this one. Yes. So I mean, this is just a way of generalized Neumann in the sense that if you take, for instance, other spaces where the whole Neumann, I mean, both Neumann boundary conditions might not be defined, you can still define just one condition plus this one. So it's a
understand this, but I'm surprised because at least in this case, all these results should have been known forever.
Okay, so first of all, as I said, so first of all, for Dirichlet, it is not immediate.
Absolutely.
Okay.
But for the Neumann, you're over.
Yeah. Okay. I mean, these cases are actually for Dirichlet in one endpoint.
Okay.
As I said, so the interesting part is that if you drop one Neumann boundary condition in one endpoint, you can get well-posed in this slightly larger functional spaces. But this is, I mean, as I will soon show that this is just the introduction to my topic, because I'm not actually interested in this kind of boundary condition.
Okay. If you had just deleted or Neumann,
yeah, okay,
then it would have been okay.
Okay. So, so as I said, so people have discovered that also center of mass is conserved in many cases. And so it was quite natural to wonder what happens if, or whether it is possible at all to replace all the boundary conditions and just impose integral boundary conditions. And in fact, it is possible, or at least to formulate the problem. So this is what I'm going to talk about in this talk. So consider the heat or the wave equation. I will show that there is no real difference in the theory. I mean, in the well-posed theory. And then you can impose, okay, first of all, the same conservation of mass condition, plus you impose that the center of mass is conserved. And the center of mass, I mean, the fact that the center of mass is conserved, as I said, so up to shifting u, you can just assume that this means that the center of mass is identically 0. And this amounts to say that this term, which means the first moment of the function u is equal to 0, but then integration by parts, you can just rewrite this in this form. Okay, so what I'm saying that is that one could at least wonder whether the wave or the heat equation are well posed, and which spaces, of course, with this plus this boundary condition, or well, not boundary but integral conditions. And in fact, this problem was considered first for the first time in the 90s, and it was solved by Buziani and some co-authors. First of all, for the wave equation in '95, and then some years later by the same authors with different co-authors in 2008 with for the heat equation. And okay, so this result is not completely satisfactory because it really very much depends on some transformations, which means that you cannot add any coefficients, you cannot play a little bit with the domain, you cannot add any lower order terms, and so on. This solution is more stable, more robust, so to say. So you can, since you are working with a Galerki scheme, then you can really improve it or generalize it to some other situation. But still, everything is related to this to these two conditions. Well, the whole idea about Galerkin schemes is that you see your PDE as a gradient flow, so to say. So basically, you take a suitable energy function or Lyapunov function, if you wish, and then you want to see your PDE as the flow of this generated by this functional in a certain space. And to do so, you need to understand which is the right space. And even if you find the right functional space, then each norm on this functional space, even equivalent norms, will give rise to different gradient flows, which means also to different PDEs. So it is necessary to determine a right functional setting for this kind of problems.
So what is non-zero here?
Pardon?
What is non-zero here? So everything is zero.
Initial state.
Yes, sure. The initial data is non-zero,
Okay,
of course.
so
So it's just a typical direct problem setting. So you have, So you have initial data, and you want to find a solution for all times, for all positive times. Okay, so if you want to find the right norm, the problem is that we will soon see that the right setting is that of a Sobolev space of negative order, and there are several possible equivalent norms on Sobolev spaces of negative order. So we want to introduce one. So to do so, let me start in this way. So first of all, we introduce, so we want to consider a primitive of functions phi. And of course, you have infinitely many primitives of a function, but you can uniquely determine, of course, a primitive if you also add this integral term here. So I mean, in this way, j of phi is uniquely determined as an operator on the space of test functions. And you define another operator p just by duality. So this is an operator acting on distributions. And the whole idea here is that you do not work on test functions over the interval, but you identify the interval, so you just glue the endpoints of the interval so that you are working on torus. And you will soon see why this is important. So at the end, you are defining an operator p working on distribution, acting on distribution of the torus. And then you can just apply, the method I'm working with is that typical of Hilbert space theory. So you just take L2 of 0, 1 as your pivot space. 0, 1 is the interval you want to study your equation on. And then you just consider the Gelfand tripole, if you wish, or just these three Hilbert spaces. So you take, you identify L2 with itself as a pivot space, as I said, and then you just take the space of, so the first Sobolev space of functions acting on the torus and its dual. Of course, this space is larger than H1 0, 0, 1, which means that this space is smaller than the typical, so the classical H minus 1, 0, 1 space. And this is important. So at the end, we will get our well-Poisson result in this space, and they wouldn't hold in a larger H minus 1, 0, 1 space. Okay, so first of all, we have some useful representation theorem for the operator p. So if you just take script I to be this operator, then p, which I recall was defined as a by duality from this primitive operator, so to say, then p takes this form if you apply it to L2 functions. And with this representation, you can soon prove that, or promptly prove some properties of this p. So the nice thing is that this p maps in a nice way these spaces in this chain. So it maps this space into this one, and this space into H101, which is a space larger than this one. But we will see that if we specify some further conditions, then you can even go to H1t. And this operator p is in some sense the inverse of the derivative, just as you would expect, of course, from a primitive operator. So let me define the moments of order n of a function. So they are just defined like this for all positive natural numbers. And then you get that the moment of order 0 can be, so this, of course, just by Hölder inequality, you can define for all L1 functions. So they are all mn, mu n are continuous linear functionals on L1, 0, 1. But there is just one of them, namely the moment of order 0, which is can also be continuously extended to h minus 1 of t. To see this, just consider this expression. And this shows why it is important to work on the space of dual functions of the dual space to h1t, because if you would be working with h1 0, 0, 1, then you would get a larger dual space, but in this space you couldn't define this duality because of course the constant function is not in H1, 0. So this is important. You are able to extend your moment to this larger space, H minus 1. And just a direct computation shows that this operator matrix is surjective. You just compute the moments, these first two moments for polynomials, and then you see that you can just fit the coefficients of the polynomials to get everything you want in C2. Okay, so as I said, you can even improve the results we had. So we had, I recall, we had that P maps H minus 1 of T to L2, 0, 1, and also L2 of 0, 1 into H1, 0, 1. You would like to reach even H1 of T, and this you can do if you apply P to those functions in L2 with vanishing moment of order 0, so with vanishing vanishing mass, if you wish. And you can even reach, so let me write this way. And you can even reach H1, 0, 1 if you also add the condition that the first moment is equal to 0. Okay. So I'm finally in the position to show which kind of norm is the correct one for this kind of problems. So H minus 1 is canonically normed by, so you can either consider just the operator norm for elements of this space, since they are just functionals over H1, or else there is a classical characterization of this space saying that the function is in H minus 1 if and only if it is of the form f1 plus the derivative of f2 for f1 and f2 in L2 in a Hilbert space L2. So we could have two different choices for a norming of the space, but then you can also prove this inequality. And since you have this inequality, you have this equivalent scalar product. So basically, you can define a scalar product on H minus 1 by taking the L2 scalar product of the primitives of the functions plus adding the moments of order 0 of these functions. And this only works for H minus 1 of T. So this wouldn't yield an equivalent scalar product, so inner product in H minus 1 of 0, 1. The proof is not difficult, but you see some of the ingredients you typically have when dealing with this kind of conditions. So let me just sketch it. So the idea is that you work with test functions, which are the distributions, the test function on the torus. And then the idea is that then, of course, you can just derivate as often as you wish. And for these derivatives, then you can transform the moment condition like this into some local terms like that. And then you can just estimate. So usually it's difficult to work with non-local integral conditions. But if you can apply them to functions which are regular enough, you do not get your locality back, but at least you can have you can work with functions where the evaluation of functions at some points, so which is more comfortable in most cases. Okay, and then the whole point of introducing this equivalent scalar product, which from now on I denote just by h minus 1t, is that you have this kind of integration by part formula. So let me comment on that. So in the classical case, you would have, of course, here the L2 inner product, and you would have here the derivatives of u and v. And you would have here the normal derivative of u and here the trace of v. And this formula is very similar to the classical one if you just replace the normal derivative by this operator matrix gamma 2 and the trace by this operator matrix gamma 1. So the proof is, of course, completely different, but once you have this expression here, then you can apply just the standard Hilbert space theory. So gamma 1 is just the this operator matrix we already found. So gamma 1 is particularly surjective, as we have seen, and gamma 2 is has this expression. So observe that if you have a u regular enough, then this is nothing but the difference of u prime evaluated at 0 and 1, so you still get some local term. And you should also observe that gamma 1 is defined on the whole space L2, because mu1 and mu0 and mu1 are, but gamma 2 is not. So you cannot define this this object in L2. So you want to go up to some higher Sobolev spaces. Okay, now you can just apply the classical theory. So the idea is to introduce a quadratic form, or more general, a sesquilinear form, and you do this in this way. So you just take as quadratic form as a leading term in the quadratic form. You take just the norm in U, if you wish, or the scalar product if you want a sesquilinear form, and then you can add some nice lower order term like this, and your form is defined on a Hilbert space, which is defined like this. So now let me explain a little bit this term. So basically what we are saying is that we are taking as in the form domain those functions L2 with moment of order 0 and 1 satisfying a certain algebraic condition, namely they have to be in a certain subspace of C2. So this kind of setting is quite common in mathematical physics, because you can show, I mean, this is the whole idea of boundary triples. So basically you can show if gamma 1 is the trace operator and gamma 2 is the normal derivative, then you can show, for instance, that all the self-adjoint extensions of the second derivative on interval take this form, as I said, for a different choice of gamma 1 and gamma 0. And what you do here is exactly the same for a different kind of condition. So basically, these forms and the operator associated with it or with them gives all the self-adjoint extensions of the second derivative with such that gamma 1 and gamma 2 are equal to 0, as we will see in a couple of minutes. Okay, but first of all, so we have a form. So there is still no direct connection to the PD we were considering at the beginning. So first of all, one can see that the form domain of this form is dense in a certain Hilbert space, and the Hilbert space is either is usually the whole space h minus 1t up to two special cases, two special choices of y, which leads to having this space here as a closure. Let me show the proof, because it is quite typical of this kind of problems. So first of all, okay, it's clear that so I only prove it for the choice y equal to 0, so which means that I'm taking the space V 0 square, which is just those functions in L2 such that mu0 f equal mu1 f equals 0. Okay, so it is quite clear that that the closure of this space is contained in the space of all h minus 1t functions having just satisfying just this boundary condition. So what's more interesting is to prove the converse inclusion, and then you just take a function which is orthogonal to this closure, and then in the classical case, so in the case of boundary condition, you would just integrate by parts. And then, of course, in this case, you cannot integrate by parts in a classical way, so you should try to help yourself as you can with what you have at your disposal. So you just try to evaluate this object here. So this is something like the second primitive of G. So at the end, you will want to differentiate this. Okay, so if you have this guy, then you can rewrite this by duality like this, and then you just are assuming that this scalar product is equal to 0 for all G in this space. And then you introduce some test functions, and the test functions here are different from the test functions in the boundary condition case. It wouldn't help much to have compact support for the function itself. It's much more useful to have compact support for the first derivative. So this is why we introduced this space here. It's important that W, the closure of W is closed in this space here, is dense in this space here, which of course wouldn't hold if you would have compact support for the function f. And then you can just, as I said before, so the idea is that if you have functions which are regular enough, then you can transform your integral condition to some difference of local terms. And at the end, since you have that this term is equal to 0, then you can just replace this term here by a difference of two evaluations of a function h. Then you apply the fact that your function has mean 0, so which you can just drop this term here by linearity, and so you end up with this term here. So which means that for all h in W, which means for all h in h1t by density, h is in the polar set of your space, which means that that you really have, so the orthogonal to this space here is just a null, so the trivial space, the trivial set in the trivial space in h minus 1 of t. So you are done, and you can do the same for different y's. So as you see, it's not really difficult, but the techniques are completely different from those you use usually to prove density of form domains or subspaces in the boundary condition case. Direct consequence of this density result is that mu1 cannot be extended by continuity to this space here, because otherwise its core, so its null space, would be closed in h minus 1 of t, but this cannot be because it strictly contains a dense subspace. So this is bad, but on the bright side, you have that you can have an estimate like this, which is pretty much what you have in the boundary condition case when you estimate the trace of a function in the L infinity norm by the h1 times the L2 norm, and you have something like this also in this case. And then this is necessary if you want to prove that your form is elliptic in the language of quadratic form theory. All in all, what you get is that you have a form with nice behavior, and you can just conclude that the operator associated with this form generates a cosine operator function. If you are not much into the theory of cosine functions, just forget about it. Just everything you want to know is that you have a C0 semigroup governing the problem. And if you're not in the theory of C0 semigroups either, just take for granted that what you have is well-positiveness of the heat and the wave equations. And the nice thing with this approach in comparison with our more direct Galerkin approach is that you have very good regularity properties of the functions, of the solution. So you have C infinity functions in time and space, which we don't have usually with other methods. And this for all y and k. So it is clear that these problems I was considering at the beginning, this by Buziani, was a special case if you take k equals 0 and y equal, well, null space cross null space. So, but what is the operator associated with the form? So this is a theorem. This is nothing but a second derivative, as you would expect, with this kind of boundary condition. So in fact, you have two complementary boundary conditions. So you impose that the moments of order 0 and 1 of u lie in a certain subspace of C2, and simultaneously that gamma 2 plus k times gamma 1 lie in the orthogonal subspace to y. So of course, these two boundary conditions together yield two conditions in all cases. So if y is a two-dimensional space, then here there is no condition, so this condition is void, but then you get here 2 and so on. So it's exactly what you would expect. And as I said, so for instance, as I already said, for y equals 0 cross 0, then you get just what Buziani was doing. If you take 0 cross c, for instance, then you get periodic boundary conditions. So you get well-positiveness of the heat equation with periodic boundary conditions. The proof is interesting, but it's quite technical, so we'll mostly skip it. I will just show you what is the whole idea behind that. So the operator associated with the form is defined like this. So basically, it's that operator for which a kind of integration by parts formula holds. And then you just want to show that this operator here has to agree with the operator I was writing down before. So you first show that this operator is included in this one, and this you do just by integration by parts, if you wish, applying this modified integration by parts formula I was showing before. So this is just this integration by parts formula I wrote down before, and then you apply the boundary condition, you apply the integral conditions you had here, or this algebraic condition actually. So because the difference of these two terms is orthogonal to this term, you can write just this one, and this is just the form I wrote down at the beginning. So you conclude that the operator B is included in A, and you want to show the other inclusion. This is much more complicated, and we'll skip it. Although, as I said, this is interesting. So everything I've said so far is well-posed in an H-1 space, which is not something you would necessarily like to work with. It's a strange space. But another nice feature of the theory of semigroups is that you can also have for free generation of semigroups, and therefore well-posedness in infinitely many further spaces, in particular in L2, taking just the parts of your operators. So at the end, you can conclude that if you are interested in L2 initial data, you get well-posed in L2 by showing that this operator generates a semigroup. So for instance, if you take so if you take y to be 0 cross 0, as in the case of Buziani, then you get you get some new non-local boundary conditions. And everything is nice. You get, as I said, so some better information about the parabolic problem. You get, for instance, existence of a heat kernel for the problem. Unfortunately, you don't get LP well-posedness. You don't get estimates for this kernel, but still it's more than you could get from other methods. So to conclude, let me just mention what happens with the spectrum of these operators. So what we already know is that for all choices of y and k, you have an operator with compact resolvent. This simply has to do with the compact embedding of L2 into this H-1 T-space. So the spectrum is purely point. And of course, if K is a Hermitian matrix, then you have a self-adjoint operator, so the spectrum is real. By standard methods based on Courant-Fisher theory, you can just have some domination resolve for the spectra of the operator associated with different choices of y and k. And in particular, you get that all the eigenvalues are negative as soon as K is a negative definite matrix. So the spectrum, even in the extremal case, the spectrum is always strictly negative. But you can show something more. This is a nice feature of this parametrization of self-adjoint operators based on this Y and K approach. Well, if you want to solve the elliptic problem, of course, you end up with a classical solution like this. And now, if you try to impose the integral conditions we were considering, then you just compute directly what are gamma 1 and gamma 2 for this function here. And you end up with this theorem. A given number lambda is or lambda square is in the spectrum of this operator if and only if you have this algebraic condition here. So if this matrix has non-maximal rank. So this is a 4×2 matrix, so this just means that this rank is not maximal. And then this is clear because if you, again, so you just want to find a non-trivial solution, a non-trivial solution of a certain algebraic problem where you just use this choice of gamma 1 and gamma 2 because you have these boundary conditions by the theorem I was showing before. So the operator associated with the problem is just the second derivative with these two integral conditions, and imposing that they hold simultaneously means that a certain algebraic system has to be satisfied. And in this way, you can even prove a nice asymptotic result for the spectral problem. So you have Weil type asymptotics. I mean, this is exactly what you expect because this holds for the second derivative with all possible, reasonable at least, boundary conditions. So it holds for Dirichlet, for Neumann, for Robin, for dynamic boundary conditions, and so on. So it is comforting, if you wish, that they also this asymptotics also holds for these non-local boundary conditions. And again, the methods to prove this are completely different from the boundary conditions case, because in that case you usually work with this with some explicit formula for the heat kernel, which you don't have at your disposal here. So what you do is the following. Okay, you can just explicitly compute, at least in this special choice. In other cases, you can somehow work by duality and then interpolate. So I want to be precise about that. But in this special case, you can just check directly that the even eigenvalues you can find them explicitly, and then they surely satisfy this Weyl asymptotic. So the problem are the odd eigenvalues. But the odd eigenvalues are given by a formula like this, with these two analytic functions. And the idea is to apply, in some sense, a sort of perturbation approach. So you just estimate this function f2 here by this function f1 here. And in this way, you can apply Rouché's theorem of function theory. And this means that this equation here has exactly as many roots as the leading term f1 in a suitably small ball. And because the first one just has one root, and you get that also this sum has one root, so you get, because for f1 you know the asymptotics, then you also know it for this sum, plus you even know that all eigenvalues are simple. So it's valuable information. Okay, and with this I would like to stop, and thank you for your attention.
So as far as I understand, one important step is to use the primitive. So it's a bit similar to the way you can relate, like, let's say, Berger's equation to the corresponding Jacobi equation in one space dimension.
Yeah, you were right.
But what do you do if you have a problem in several space dimensions?
This is a very good question. Okay, so let me say so. I am aware of some people who have tried to generalize this kind of problem to a higher space dimension. So you could see these integral conditions as conditions on a sort of kernel operator, so integral operator with a kernel, with a trivial kernel in this case. And of course you can consider more general kernels, and in this way you can extend it to higher space dimension, but it's not exactly the same. And otherwise I'm not aware of any extension. Actually, I'm trying to find the right generalization, the correct generalization, but I'm not able to find them. The problem is that, you see, if you have, say, Dirichlet boundary conditions, you go from two boundary conditions in the one-dimensional case to infinitely many, of course. So you have the conditions are given by an infinite dimensional space, so to say. In this case, I have no idea how you could formulate moment conditions for a square, say, even for a square.
Maybe it's possible that you would have to consider some sort of integral operator which maps the unknown into some function on the boundary. So you have a lot of freedom.
This is exactly, this is the whole idea of having this integral operators with a core, so with a kernel, for a non-trivial kernel, but then it's not quite clear to me why they are related exactly to this conservation of center of mass in this one-dimensional. I mean, you can of course formulate them, but in some sense they seem to be artificial. So I have no idea whether it's possible to do so. Probably I would guess that it's simply not enough. So just two conditions. The problem is simply not well posed if you just impose conservation of mass plus center of mass.
If I recall, in this paper by Cannon, you mentioned it was like heat equation subject to the specification of mass.
Right, of energy.
Of
it's the same, of
yeah.
course.
So it wasn't zero, it was a function of t here.
Yeah.
Exactly. And also the upper limit may not be 1, can be some free surface, like a Stefan. Is the same goes through?
Okay, they have, I have two answers to that. So one of the nice properties of semigroups approach is that it doesn't matter at all whether you are considering homogeneous or non-homogeneous conditions. because what you do is the following. You can show that an operator generates a semigroup if and only if an operator matrix like this generates a semigroup, and if you consider the Cauchy problem associated to this guy, you get something like u d dot is equal to a, so in this case it would be something like gamma 1 of u, 0, 0, 0, u, gamma 1 of u, so which means that so having a solution, okay, and then you can add some inhomogeneous term like, so this is also by just applying the variation of parameters formula for the semigroup, you can show that this problem is well posed, and this is nothing but u dot equal au plus f okay, if you wish, plus f1 of t, this can be 0, and then gamma 1 prime of u of t is equal e2 of t. So if you just integrate this, you get an inhomogeneous condition for this for gamma 1. So this is not a problem at all. The second question is more interesting. I mean, the answer is more interesting. I have no idea. So what kind of was considering is a condition like this. So 0 and then some function of t, right? So something like I don't know. I mean, he doesn't, as far as I remember, he doesn't get. I think he only gets uniqueness in this case. He doesn't get well posedness in general. It would be interesting to have some information on that, but I don't. I mean, the whole idea here is that this integration by parts formula hold, and of course this can only hold for a certain function s. So I don't know.
So, just concretely, the problem you started with the Dirichlet condition at one end and the integral equals 0 condition. What is the final result about that?
I don't consider that one. So it was just
that's not included.
right. So as I said, so the idea is people started with that one, and then they realized that it is not necessary to have a mixed boundary condition. They can even just forget boundary conditions and just only impose integral conditions and only integral conditions.
Okay.
And then this is everything I've done, so to say. So I've generalized. So I was considering at the beginning this double integral condition by Buziani. So it was conservation of mass plus conservation of center of mass. And then I've shown that these two conditions embed in if you wish, infinite dimensional manifold of boundary condition or integral conditions containing that special case in particular, and all of them yield a well-posed problem. But I'm not able, not yet at least, to find a connection to these mixed problems. So I've shown that if you take a restriction to some L2 spaces, you also get some mixed problems in some case, but in general, there is no clear way how to consider arbitrary mixed conditions. In particular, I'm not able to consider Neumann plus conservation of mass. This I cannot do. Or Neumann or Dirichlet plus conservation of mass.
Okay, and there is no.
I have no idea how to do that.
Yeah.
Maybe I can make a remark related to those two very nice questions. Maybe it will be interesting for you. I send you a note, but maybe you didn't appreciate it. Okay, so the remark is related mainly to your question. So again, all right. So first of all, I'm a little bit opposed to this non-local business, because at least the two problems that they were posed on the board originally are both local. Namely, they give rise to the problems ux1 and this ux1 and t minus ux0 t, and if you want to put non-homogeneous boundary conditions, you have this some f1 of t, and the second is u of 1t minus u0 of t minus ux0 t equals f2 of t. And these two were precisely the basis of your scalar product, etc. So first of all, forget about the non-locality, is a combination of simple Dirichlet and non-boundary conditions. So what is difficult about this? It's difficult because, as you know, you don't have self-adjoinness, so the spectral theory is more complicated, etc., etc. There's an old story about this, and if you recall, there was, for example, a classic in the 70s, people looked at this very carefully. There was this boundary condition ut plus alpha ux plus beta u, but on the semi-line equals something given, and then Cohen introduced these pairs, like here, to avoid the problem of self-adjoinness, etc. Again, this is a very nice setting that the speaker has shown us how to do it. If you want, perhaps non-trivial remark is that all this can be avoided in the following sense. You see, we have introduced recently a method which doesn't care about spectral theory, etc. So directly gives the solution to these problems. And if you want, of course, because you do it at the higher level, you can go and see what it means at the level of spectral theory. And this will give you the spectral representation associated with this. We haven't done, of course, for this problem because I didn't know about this, but we have done for this problem, and I have zero doubt that this will work. And so you can, from this new method, understand what kind of combinations of boundary conditions give you well-posedness, but in this case, if these coefficients are constant, that's why it will not work. In the case of the Stefan problem, you will have an explicit representation of the solution, and furthermore, the advantage of this new approach is that it can work for any order, not just for second order. For example, you can go to pose a similar problem for a third order, and now, but you see, until now, I didn't have a good motivation for this combination. So I'm very happy because the non-local condition is much more physical than this. So now we have at least a motivation why we have been studying these problems. And for this, I'm very grateful to the speaker.
So you get parabolic information or spectral information?
You see, you get an explicit representation of the solution, and from this you can go down and find out what it means at the level of the spectral theory, and you will get explicit information on the eigenvalues, not just asymptotic information. But
well, let's thank our speaker again.